This lesson is section 2 of unit 2, the power rule. In this section, we're going to talk more about the derivative. And we can think of the derivative as being three things. It can be the slope at a point on a line or on a function. It can be the slope of the tangent line, or it can be the instantaneous rate of change. All right, so let's look at this function here and notice what happens when I'm looking at the tangent line. Notice how the tangent line just moves around. At sometimes it's positive, at other times it's negative, and at certain times it's 0. So like right there it's 0, then it's negative, it's 0 again, then it's positive. All right, we learned the basic definition of the derivative, but now we're going to learn some of the shortcuts. And the first of these is going to be the power rule, okay? And the power rule simply says that the derivative of x to the n, okay, where n is the exponent, you bring the exponent down in front, that becomes the coefficient, and you decrease the original exponent by 1. So the derivative of x to the n dx is simply equal to nx n to the minus 1. Now notice, this only works, all right, if f of x is equal to x to the n or y is equal to x to the n, okay? So we can use this rule, the power rule, in either of these cases, okay? So basically, our function has to be x to the n. So let's look at some examples. In these examples, I want to find the derivative of the following functions. Let's look at the first. We got y equals x to the third, and the second is y equals 5x to the fourth. So y equals x to the third, dy dx, therefore is we take the exponent, move that down in front, and we decrease the original exponent by 1, and so the dy dx of x to the third is simply 3x squared. Now, let's look at more examples here. We've got f of x is equal to 3 over x squared, or f of x is equal to the square root of x. So the first thing we're going to do is we're going to rewrite these. So 3 over x squared is going to become 3x to the minus 2. Notice we take this positive exponent in the denominator, we bring it up to the numerator, and we change the sign. And the square root of x, remember we can change that to being an exponent, and that becomes x to the 1/2. So we've rewritten these, and now again we can use the power rule. So notice, now we take our 3x to the minus 2, we keep the 3, we bring the exponent down, that's the minus 2, all right? And we decrease the exponent by 1, and that makes it minus 3. So minus 2 minus 1 becomes minus 3, or the derivative becomes minus 6x to the minus 3. Now, obviously, we could take this, and we could take and move it. We could take and move the x to the minus 3 down to the denominator, and it could become minus 6 over x to the third. All right, so let's look at our x to the 1/2. The derivative of that, we're going to take the exponent, the 1/2, that comes down in front here, all right? X, we're going to make the exponent now 1 less, so it's going to be 1/2 minus 1, or it'll become x to the minus 1/2, all right? Or we could, again, simplify this to be 1 over 2 times the square root of x. All right, here's another example. Find the derivative of the following. F of x equals x to the fourth plus 5x squared minus 6x plus 1. So how are we going to handle this? Basically, we're going to handle it by looking at each term individually. And if we treat each term individually, our x to the fourth simply becomes 4x to the third, and our 5x squared becomes 5 times 2, or 10x to the 1 less, which would be 10x simply. Our minus 6x becomes minus 6, and of course the derivative of a constant is simply 0, and here is our derivative. Note, the derivative of the sum or difference of functions is the sum or difference of the derivatives. So basically we're going to take the derivative of each individual term and then sum it in the end. So let's look at still some more examples. So in this first case, we want to find the slope of this function at a particular point, x equals 2, all right? So let's see, how would we handle that? All right, so we're going to take the derivative of each individual term. So this first term is going to become 3 times 2, or 6x squared minus 1, all right? So that's the derivative. But we want to know the slope at x equals 2. So I'm going to take the derivative and plug in x equals 2, and I come out with the answer. The slope at x equals 2 is positive 23. Now let's look at the next one. Find the equation of the tangent line to this function at x equals 2. All right, so we've got the same function, right? So therefore we know the slope at this point. The slope is simply equal to 23. All right. Now, so now let's take the original function and plug in 2 and see what the y value is at x equals 2. So if I take the original function and I plug in x equals 2, I come out with the y value is 19. So I know the x value is 2, the y value is 19, the slope is 23. So I can find the equation of this by simply plugging into an equation and finding out that this is the point slope form of the equation. Y minus 19 is equal to the slope 23 times x minus 2. So there's my equation of the tangent line to that function at x equals 2. Now I obviously can change it into y equals mx plus b form. Regardless, it doesn't matter. This is the equation in whatever form you want it to be in. Now remember when we talked about derivative in the beginning of this lesson, we said that it could be the instantaneous rate of change of a function. So find the instantaneous rate of change at 3 seconds, okay? So we're given the displacement. This is a displacement function, and we want to know the instantaneous rate of change at t equals 3 seconds. Okay, so first thing I'm going to do is take the derivative of this function right here, all right? Take the derivative, it becomes minus 4.9 times 2t plus 40. So here's my derivative, okay? Now, at 3 seconds, if I plug in 3 for t and crank all the numbers out, I come out with the instantaneous rate of change at 3 seconds is 10.6. Now, whatever the units are of s per second, okay? So that'll be the instantaneous rate of change at 3 seconds. So you can see the different ways we can look at derivative. We can look at it slope at a point, the slope of the tangent line, or we can look at it as the instantaneous rate of change.